The first is, everything you need to know is in the instructions. The second thing is, this is a record-keeping thing as much as anything else, and there's additional difficulty here. With the air card conservation of momentum, you had to keep track of before and after velocities. You had to do some calculations, and there was a lot to keep track of. Here, there's even more to keep track of, because we're going to have target velocities. You're going to try to get a cart moving at a certain speed, but it's not actually going to move that speed. So you have a target velocity that you need to keep track of, and you also have an actual velocity. So if the target is 0.3 and you get 0.28, you got to keep track of both of those numbers. Yeah?
It says we can't access that until Monday.
Oh, well, that's too bad. Okay, thank you. I'll fix it, but I'm not going to do it now because otherwise I'll get too out. Okay. And then the other piece is that you're going to be making predictions and then evaluating your predictions with real data. And those aren't going to be the same either. If you predict, for example, oh, cart 2 is going to move at 0.62 meters per second, it might actually move at 0.47 meters per second. So now, in addition to having V1 and V1 prime, V2 and V2 prime, you also have actual V1, actual V2, actual V1 prime, actual V2 prime. You're doubling your numbers. You have to keep track of all of it. I've made a data table here that's got all the information in it, but if you don't understand what information you're putting here, you're gonna get garbage, right? So I've got target velocity, actual velocity, I've got predicted velocity, I've got measured velocity. Like, I know what that means. You need to know what that means as well. That means you've got to read the assignment really carefully. I'm going to walk you through a trial so that you can see what it's going to look like. The trial that I'm going to do is going to be one that, let's see, 1.3, 1.3. Okay, I'm going to do, it's not on here, okay? So I'm going to do an elastic collision between these two carts. And my cart on your right is this is yellow. My cart on your left is green. I know that those aren't what the colors look like to everybody, but that's what graphical analysis says they are. So I'm recording this, and this is going to be kind of like one of those tracker things, where if you're super tech savvy, this is going to be relatively easy for you. If you're not super tech savvy, then you are probably not going to be able to do this on your own by reading the instructions or just watching me do it and half listening now, which means you have to do two things. One, listen really carefully. Like, watch what I'm doing and think about it. So those of you who are back there goofing off on your computers, stop. When you come to me and say, Brigar, how do I get the cart set up? I'm going to tell you to watch the video. So watch now, and then the video will be posted in 15 minutes, and then you'll have that as a reference as well. All right, so there's a lot to think about here. I'm just going to talk about elastic collisions today. We'll look at inelastic collisions on Monday. And so the first thing you have to do is get carts of different colors. Graphical analysis keeps track of the colors. So if you have two carts of the same color, it's going to be harder for you to figure out which cart it's talking about. So I have one green cart, and that is, as far as you're concerned, the left-hand cart. I have one yellow cart. As far as you're concerned, that's the right-hand cart. I am going to keep track of all of this the same way that I suggested that you all keep track of things. So I'm going to set up my my little system where I have, there's something is going to pop up here in just a second. I apologize in advance. Clicked twice, didn't mean to. Okay, so I have my left-hand cart, I have my right-hand cart. There's going to be a collision. I'm going to have my left-hand cart again. I'm going to have my right-hand cart. Okay, and to figure out the velocities, I'm gonna kind of execute, okay? So here's my setup. I'm gonna have my left-hand cart, my right-hand cart, and I'm gonna roll the left-hand cart into the right-hand cart like this. I'm just gonna roll it like this. Okay? And I'm gonna try to get it to move at about like half a meter per second. So this is half a meter right there. So that's gonna be a half a meter per second. And now after the collision, I can see my right-hand cart goes this way, my left-hand cart goes this way. So I know after the collision, it's gonna move like this, okay? And I'm gonna write the masses in here. I'm gonna write them below as well, but I think it's gonna be easier for me to write it in here just so I can kind of visualize what's going on. My left-hand cart is just a cart. That's about 0.3 kilograms. My right-hand cart has a cart with 2 bars. That's 1.3. About. And that's good enough. Okay, so what I tried to do, my target velocity there is about 0.5 meters per second. So my initial cart mass is 0.3, my initial cart 1 velocity is about 0.5 meters per second. And I'm gonna revisit this because when I actually do this, this isn't gonna be right. It's not gonna be right. My mass 2 is 1.3, its initial velocity is 0. Okay. After the collision, mass 1 is still 0.3. I don't know how fast it's going. And after the collision, mass 2 is still 1.3, and I don't know how fast it's going either. If you think about the equation that I showed you on Tuesday, there's 6 variables. Right now, we're missing 2 of them. We cannot make any predictions about this system. For this activity, we're going to do the same thing every time. First, we're going to measure the velocity of this cart, the one on the left. Then, we're going to predict the velocity of the cart on the right. And then, we're going to check our prediction by measuring it. And so you can see already, like, the record keeping is going to be a nightmare. Keeping all this stuff straight in your head is the tricky part. What happens with this activity is people who are only sort of half listening or half thinking about what's going on end up bonking cards together, writing down a bunch of numbers, doing a bunch of math, and completely missing the point, which is if we measure / know some initial velocities and one of our final velocities, and we know the masses involved, then we can reasonably accurately predict the second velocity after the collision. So we're just setting things up so that we can make a prediction. In order to do that, we have to have 5 measurements. We have to have 2 masses, we have to have 3 of our 4 velocities. But one of those velocities that we're going to measure is a target. So I'm going to do my best to try to get this one to move at about 0.5 meters per second. One of the velocities we won't know until we measure it. And one of the velocities we're both going to predict mathematically and then measure. So there's a lot that you have to do to get there. All right, so let's get graphical analysis up and running, and if you do this the way that I did, what you're going to see when it scans for devices is the 2 carts nearest you. One is going to be yellow and one is going to be green. They end in Y for yellow, G for green. That's why I call this one yellow, even though to me it looks more green. And that one is green, even though to me it looks more blue. Did this one turn off? All right. And then because the record keeping is going to be challenging enough as it is, I'm going to think about this in terms of left and right. My left cart is the green one. So on this top graph, the information I'm going to need is its velocity. And on the bottom graph, that's going to be for my yellow cart, and the information I need from that is its velocity. another confusing thing. So again, if you're not locked in, you're gonna get confused when you start seeing this. This says position Y, or position Y, velocity Y, acceleration Y. What does that mean? Yeah, up and down, right? Wrong. In this case, I know, it's really annoying. These carts are one-dimensional measurement systems. There is no Y dimension with the carts. This Y means yellow. This G means green. Velocity Y is telling me nothing about its up and down motion. Velocity Y is telling me the velocity of the yellow cart in its X dimension. Sorry that that's what they did, but that's what they did. We don't have any choice about it, all right? So if I I'm just gonna like collect some data so you can see what it looks like. If I roll these two carts together, then I can see some stuff. So let's see what's happening here. So here, it looks like they get really close to each other here. So this is the collision, right? So they are moving closer and closer and closer to each other. They collide, and then they bounce off. Does that look right?
Yeah.
That was when you put it.
Yeah. This is a position graph. This is a velocity graph. So each cart, I have them lined up so that the positive direction is to your right. My green cart, its positive direction is this way. My yellow cart, its positive direction is this way. It's insane how much stuff you have to keep track of here. That's going to be the best way to do it. That means our positives and negatives are going to be aligned. What does this information show me? It shows me that my green cart is moving in its negative direction here. That's me moving the cart this way. Here, the yellow cart is moving in its positive direction. That's me moving the cart this way. That's not the collision. Then I push them toward each other. My green cart starts moving in its positive direction. My yellow cart starts moving in its negative direction. When they cross 0 is when they collide. Okay? When they both are at 0, they're in the same point at the same time. That's when they hit, right? I'm messing with you again. Why aren't they both at 0? Isn't this the same place, TJ?
0 where the cart started?
0 is the individual carts. They each have their own 0. Oh my gosh. 0 is not where the carts collide. 0 is when they're back where I started, not in really, even not really, because this is velocity, right? This is when the cart is motionless. And then this is me continuing to speed it up, the green cart in its positive direction, the yellow cart in its negative direction. These lines right here are what you're looking for. This is relatively constant velocity. For my green cart, it's in its positive direction. That's when the cart is moving like this. My yellow cart, at the same time, is moving with a relative constant velocity in its negative direction. The yellow cart is sliding this way. This right here is the collision. The green cart reverses direction and then starts moving at a relatively constant velocity in its negative direction. The yellow cart doesn't reverse direction, but it slows down. And it continues moving in its negative direction, just more slowly. Okay, watch what happens. The yellow cart is still moving this way in its negative direction. Interpreting these graphs is critical. If you look at this and you think, oh well, here's the collision, or here's the collision, or here's the collision, your data is going to be garbage. The collision signal always looks the same. There's going to be relative constant velocity and a relatively short, smooth curve between them for each cart. The green cart reverses direction, the yellow cart doesn't, but either way, that collision is a relatively short, smooth curve that connects one mostly constant to another mostly constant velocity. Okay? So let's do it again, and this time, let's try to kind of get our setup. So our setup ideally is the green cart moving at about 0.5 meters per second, so that's, I think, about that. The yellow cart is motionless, okay? So I'm going to put my yellow cart here, and I may need to do this a couple of times. to get it right, but we'll see. All right, so I'm gonna get my green cart. That feels like about half a meter per second. How close did I get? Well, so it's a little bit less than that because this is the collision and it sort of slowed down. 0.5 would be right here though, so let's try it again. I'll try to get it a little bit slower this time. That's pretty good. Let's go with that. So here's me moving the cart back and forth. Here's the collision. Right before the collision, my green cart had this velocity. If I highlight that and I choose statistics, it will tell me the average. And the average here, oh, wait, that's way fast. Sorry. That was way too fast. I gotta do it again. Sorry, I read my graph wrong. Gotta do it again. Wait. All right. Well, we might call that good. That's not good enough. I would keep doing it, but I don't want to waste your time. So let's look at this. This is going to be more like 0.6 something. 0.63 about meters per second. So when I go back to my data, my target velocity was 0.5. My actual velocity was 0.63 meters per second. You should get closer than this. It might take you several tries, but you'll get it, okay? And then my green cart, after the collision, I'm gonna measure its velocity from graphical analysis. So that's gonna be down here after the collision. The average velocity is about negative 0.25. So I'm gonna put that in here. Negative 0.25 meters per second. And this information is what I'm going to use to make a prediction. Okay, so I'm going to go to the conservation of momentum solver, which I've posted for all of you. And I'm going to put in the actual data that I have up here. There's going to be one missing item. Yeah.
I was going to ask if you want to say it's theoretical or actual.
Yeah, no, use the actual. Use the actual. Let's see, make this. Okay, so my first object, the green cart is 0.3, yellow cart is 1.3. My green cart was moving at about 0.63 meters per second. My yellow cart was not moving at all. After the collision, my green cart was moving at about negative 0.25. And then I'm gonna click here, and the conservation of momentum solver will tell me a predicted final velocity of about 0.2. So let's see how we did. My predicted velocity here is 0.2 meters per second. That's based on this 0.63, which was the actual velocity of the first cart. Let's go back to graphical analysis and see what it tells me. I get 0.18, so not too bad. It's not perfect, that's pretty darn good. That is within 10%, right? Like, in fact, that's exactly 10% slower than what I predicted. A couple other things to think about here. Number one, the track needs to be level. I carefully leveled this track yesterday before I used it. And you know it's level if you put the cart pretty much anywhere and it doesn't start rolling. This is good enough, right? There is friction acting on the cart. You can't get rid of that. But what we don't want is for there to be an overall gravitational force toward one or the other end of the track. If there is, there's an overall force on the carts in the direction of the collision. You're going to see the overall momentum of your system increase or decrease accordingly. It'll mess everything up. The second thing is, in the assignment, it's asking you to look at a couple of elastic collisions. You can set those up the way that I did with the springs, and then a couple of inelastic collisions. To get an inelastic collision, the carts have to stick together. I have Velcro for that when you're ready, but we won't be doing that, I think, today. We'll look at that on Monday. And then the last thing is, I still want to do I have this idea that I want to try, but I'm not going to do it for you right now because I've already talked way too much. I'm going to shut off the recording. I'm going to let you all get to work. Your job today is to start getting some good data. It's going to just take some playing around first, though. You can use these carts in this track if you want to. Let me know if you have any questions. Best of luck to you.